Hello everyone. We'll be discussing about the shear strength tests in this session. There are four tests, and we'll be discussing two tests in this session and also respective problems. Okay, this is called direct shear test, the first one. The laboratory arrangement will be like this. Here what you can see is this hatched one is external box 11, that is container for shear box, container shear box. You got a rollers here, 12 rollers, so that it is free to move without any friction, this particular box. Inside that you got actual shear box, whatever direct shear test is called. It is also called as box shear test. Let me write that. So it is also called as box shear test, right? So that box is nothing but this number 5, whatever they have written here. Number 5 or 8, upper part of the box and then lower part of the box. This 5 is indicating something else anyway. This particular one, which is here, so this is the upper part of the box, and then this is lower part of the box. Number 9 is lower part of the box. Actually how it looks is like this: a box with the thickness, a hole kind of thing inside. Okay, that is the way how it looks. So there is a box with a hole, you can say. That's how it is. So when you cut, obviously what you see is only the sides, and it is open from the top as well as the bottom, through which all these arrangements will be done, right? So this is called upper box. Exactly similar way there is a lower box. They fit one onto the other properly, and then care is taken that hardly there will be any metallic touch between them, so that no friction is there, right? And overall arrangement is something like this. I'll try to explain first there itself on the board, and then we'll see. I'll remove this here. So you got a upper box and lower box, and here 6 is nothing but soil. The soil is held between this 5 is grids, so that it won't slip. The upper half is, look here, upper half is connected through this yoke. Number 10 is a UR, which is fitted to the upper part, right? And then 14 is attached to resistance. Okay, then this container is pushed. 13 is shear force applied. So what you have is a soil specimen, which is half of that is present in the upper box, half of that is present in the lower box. And when you place it, all the arrangement is done, and then try to push this lower half, and you are holding back by a resisting force, shearing resistance. So what you measure is the resistance to shear along this particular dotted line. That is what is happening, right? So that is resistance, and then this is upper load or vertical load. So on this plane of the shear, there will be a normal stress which is perpendicular to the plane of shearing, and also there is a shear resistance. Okay, so the soil is held between the grid plates. The 5 is metal grid plates. The 4 are porous stones, 4 are porous stones. Above that you got a loading pad. Number 3 is loading pad. Number 2 is a ball centrally placed so that the load is uniform. Number 1 is loading yoke. In the sense the vertical load is applied through this. You know that in shear, more the direct shear, more the normal reaction, there will be more of frictional force, because mu into nr becomes a frictional force. So we'll be testing for various loads, vertical loads, at least 3 to 4 of them. So this is for application of normal load. And then when you apply a force, this is not measured. Actually a push is applied, but resistance per shear is measured at point 14 through what is known as proving ring, right? So here when the force is applied to move it, actually we are trying to shear the box, and then we are not measuring the force over here. We are just applying gradually so that this slides off, and the resistance is measured at 14. That is the procedure. Now the same procedure is in detail in written in detail. We'll go through quickly. Direct shear test box shear test. The size of the soil specimen used in the test is 6 centimeter. So here inside the box you got a size of 6 centimeter by 6 centimeter, so that area of resistance across this shear plane is 36 centimeter square, and thickness is about 2 to 2.5 centimeter, 1 centimeter on that side, 1 centimeter on this side. That's how the shear specimen of soil is used. The direct shear test equipment essentially consists of shear box, so that is what is upper and lower box, the loading yoke for applying normal stress, geared jack for applying shear force. This one, it is geared or manually it will be pushed. There will be arrangement for manual application of the push also. Then there is a facility to measure the shear force, that is at 14. Facility to measure the shear force, and there will be what is the vertical movement and horizontal movement, that will also be measured through dial gauges. That is what is essentially the basic arrangement of shear box test. We'll go to the next slide. So here the shear box consists of two halves, upper and lower. The lower half is in contact with the shear box container. Lower half is in contact with the container, which freely slides on the rollers. This container is applied with a constant displacement. 13 is for application of the load, so that it is continuously pushed at some particular rate, maybe 1 millimeter per minute, or 1 millimeter per 10 minutes, like that. This very slow motion would be there, motorized motion, or even manual rotational motion with gear system, so that this push is very slow, very gradual. Okay, the soil specimen is placed in the shear box such that it gets sheared on horizontal plane exactly at its mid height. That's how it is placed. The specimen is sandwiched between a pair of metal grid plates and a pair of porous stones. Metal grid plates, so that the soil will not be slipping, right? That's why there are grids which are perpendicular to the plane of board. Over here the grids, you can see actually striations, which are lines which will be holding or catching the soil like that, so that it won't slip, right? Porous stones, so that if it is wet, if it has to put the water out, there is a possibility that it will allow the water to goat also. The plates have serrations, that's what, lines, to be placed at right angles to the direction of shearing. So you can see that these lines are being seen, right? They are perpendicular to the plane. That's why they are seeing like a grooves, and shearing is done in plane horizontal. 13 to 40, you can see that is the line of shear, and this is perpendicular to the plane of paper or board, right? So that the soil specimen is gripped properly. Okay, next. For conducting drained test, generally what is done is drain test, because whatever wet soil is there, when it is applied with a load, directly the water goes out. You don't have any control so that water is allowed or not allowed. So it is always a drain test in case of direct shear test. For conducting drain test, perforated grid plates and porous stones are used. Okay, here perforated in the sense, here all these things will be having a hole so that the water goes out of porous stone and through the plates. In normal stress, this is main part. In normal stress, sigma is applied on the specimen and kept constant throughout the test. So here when you apply, there will be application of normal stress, and it is of some magnitude sigma. Normal stress maybe 10 Newton per millimeter square, or something like that. Some particular value is applied. As the lower half of the box is pushed, means when you apply force at 13 to push, right, the resistance developed by the soil is transmitted through the soil to the upper half of the box. Means when you push it, this try to uh, take everything, right, and that resistance is measured over here, right, the, to the upper half of the box. This upper half of the box is bearing against shear force measuring device, so that is 14, such as proving ring or dial gauge, and the resistance is measured. As the lower half is displaced continuously by application of force at 13, the shear resistance also increases until the specimen fails. So gradually here resistance will be more, because this is trying to go this way, but this is held in position by an application of force measuring device. This is not allowing it to go this way, but the lower half is trying to go this way. So that shearing resistance along this plane is measured through a force, right? So test is conducted preferably on the specimens by plotting tau f on 3 specimens, and plotting is done. Tau f means maximum shear resistance, which we call it as shear strength, against normal stress. The failure envelope is obtained. The cohesion C and angle of internal friction phi are measured on the plot. The shear box test can be either strain controlled or stress controlled, but generally it is strain controlled, in the sense, here this container and lower box is continuously applied with a specific speed, in the sense, as I told you, 1 millimeter per minute or 1 millimeter per 10 minutes. That is how the speed is applied, and it is continuously pushed. No force is applied, in the sense, no force is not measured and applied. It is a motion is applied continuously, whereas here the resistance is measured. That is why what we have in control is strain, means the motion is under control. That's why it is strain controlled. Otherwise you can conduct stress control, where the force applied is directly measured, but generally we conduct in the laboratory strain control test. Means what we have in control is the motion or the rate of motion. Resistance of it is measured. strain controlled. Strain is increased at a constant rate and the stress is measured. In stress controlled test, the shear stress is increased at a constant rate and strain is measured. Okay, here let us imagine that we have conducted a test in the laboratory. I am solving the problem, right? A series of direct shear tests were conducted on a soil with following results being obtained at failure. Serial number 1, 2, 3, that is test number 1, 2, 3. The normal stress applied 15 kilonewton per meter square and it has failed at a shear stress of 18 kilonewton per meter square. I told you in the earlier case that you have to apply some sigma and then measure the shear force. The shear force divided by 36 centimeters square will be giving you the stress. Similarly, the force applied divided by cross-sectional area gives you the stress. So those failure stresses are directly given over here. When you apply 15, it requires 18. When you apply 30, it requires 25, like that, right? Determine the shear strength parameters C and phi. So cohesion and angle of internal friction are referred to as parameters. Draw Mohr circle and determine principal stresses and direction of principal plane at sigma equal to 30. That is what is the problem. Okay. Here you have to take some scale because it is a Mohr circle, and then normal stress is measured or plotted along x-axis. The shear stress is plotted along y-axis. I have taken some scale. I have drawn this in AutoCAD so that you can also, if you have a facility, you can draw this in AutoCAD, or in the examination anyway you have to draw it on the graph sheet only. Best is you try on the graph sheet. Take some scale. So here we have 15 normal stress, 15 along this axis, 18 along y-axis. So when I measure 15 and 18, here there is a point. I have called it as point number 1, right? That point is having 15, 18, and you've got 13 to 30, 25. So you got 30 on x-axis, 25 this way. So there is a point here, 20, the coordinates 30, 25. The third point is 45, 32. So I got 3 points. So as far as plotting is concerned, direct shear test is very simple. You will be getting points like that. You insert a straight line curve. So there is no point in even if it is a slight deviation is there here and there, approximately you have to fit in a straight line. So here I would like to give you an idea. Suppose if you have got 1 point there, 1 point there, 1 point there, so you cannot fit a straight line. So approximate straight line means what? It is like that, means this is also slightly away on that side, this is also slightly away on this side, and one is passing through, right? So like that, averaging out, you got to draw a line. So that way you have to fit in a line. Done that. This. Okay, I have drawn this line. Now care has to be taken, very important care has to be taken, that you have to plot both the stresses at the same scale, because we are trying to draw a circle which is 2-dimensional figure. So you cannot have different scales for this axis and this axis. You have to have same scale on both the axes. That's one point. Okay, now if you measure the angle made by this line with respect to horizontal, here I have put in the angle 25.02 degrees is nothing but angle of internal friction phi, and the intercept on y-axis here, it is measuring 11 kilonewton per meter square, is nothing but cohesion, right? I think that is easy to understand. Simply draw the points, fit a straight line. The angle made with horizontal is phi. So let me write that value. The phi over here is 25.02 degrees, say 25 degrees, and cohesion, the C, is equal to 11 kilonewton per meter square or kilopascals. So that's how the results are written very clearly at the end of the problem. Okay, then here draw more circle and determine the principal stresses and direction of principal planes at sigma equal to 30. So you have studied now what is Mohr circle and how to do everything. Here, this particular point, which is indicating 30-25, right? The plane on which 30 is applied, let me draw that soil specimen also so that it is easy to understand. In direct shear test, you know that it is like that, and normal stress is applied that way. There will be resistance, normal reaction, and shear is applied at the lower box. The resistance is there on the upper box, that is shear, right? Now this particular specimen of soil has got horizontal plane on which there is 30-0, 30-25, right? So that is the plane. So that plane is represented by point 2. Then when I draw a line parallel to that over here, what I get on the circumference is OP, origin of planes. You have studied this, otherwise you have to go through earlier Mohr circle videos. OP is there. Now origin of planes is over here. All the planes originate from here, and the point A indicates major principal plane, point B indicates minor principal plane. The inclination of the planes will be nothing but the angle made by OPA and then OPB. Those are nothing but major principal plane on this axis, right, and minor principal plane along this. Now what is the magnitude of major principal stress? It is nothing but from O to this point, and that is what is written here. 69.25 kilopascals would be the major principal stress, and O to B, that is 14.08 kilopascals, is minor principal stress. And if you want to show those stresses, you can show it like that. This part anyway. So here I have shown the shear box itself. So this is normal stress, the shear stress applied. So this is the plane parallel to this, and it makes an angle of 57.51 degrees, and the other one will be making 32.49 degrees, and that is that line. OP to B is this line. So that's how we can plotting, finding out C and phi, and also finding out origin of planes, the inclination of principal plane and principal stresses. Okay. Next problem. In a direct shear test on sand, the sample failed at shear stress of 70 kilonewton per meter square when normal stress was 100 kilonewton per meter square. So sigma and tau combination at one failure is given. Determine the angle of internal friction. Determine the major and minor principal stresses. Mark the major and minor principal planes on Mohr circle. The similar kind of problem, but slightly different. I'll tell you what is the difference. If you start reading in a direct shear test on sand, when it is sand, this is where you have to take care of the wordings. When it is said sand, the cohesion is automatically 0. there is no cohesion as far as sand is concerned. So indirectly they have mentioned that it is C equal to 0. Now they give a normal stress, sigma is given as 100, tau is given as 70, right? Now what is the relation between sigma, tau, C and phi? You have studied that. So that relation has to be used. We have proved that relation in the last class, that is sigma 3 is equal to Ka sigma 1 minus 2c root Ka, right, where Ka is a function of phi and it is equal to 1 minus sine phi divided by 1 plus sine phi. Okay, now using that relation one can find, because C is anyway 0, sigma and tau are given, the only unknown is phi. We'll see how to solve it. Okay, that's how the data is given. I've written the data. It is sand, that's why C equal to 0, tau f equal to 70 when sigma equal to 100, phi is asked. So draw more circle, major and minor principal planes, stresses on planes. Okay, here I'll put this relation tau equal to C plus sigma tan phi. This is equation of that line, right? So when you draw the here, so when you draw the Moore's envelope, right, so equation of this line, you have seen that it is tau equal to C plus sigma tan phi. From this also you can find out straight away, because given 70, C is 0, sigma is 100, tan phi equal to 0.7, phi equal to 35 degrees. Okay, now even if you draw this more circle, it will be like this, right? Now how to draw? Look at this. This is tau axis, this is sigma axis, that is normal stress axis. You got only one point. Look at this, only one point. At a point 100 normal stress and then 70 shear stress. You can just see here I have measured 70 here, 100 on this axis, so that is the point, right? But C equal to 0, that's why this failure envelope should go through origin. So that's why I can draw this line from origin and then through that point, like that. Okay, that is how this line is drawn. Okay, now you have to find out the angle there. If you can draw this on a graph sheet directly, you can measure this angle with a protractor and give. Otherwise, if you are doing it analytically, you can use the geometry over here and then try to find out angle phi. What I have done is I have drawn a line perpendicular to this tangent, which is a radius, right? So sine 55, what I have written is the angle is 55 because okay, okay, here 35 is taken from this itself, and when you have 90 degrees, that is tangent, and then a radial line is 90 degrees, 35 here, it should be 55 here. So if I call this as y, which is 70, this I don't know, x, let me calculate. So sine 55 is equal to y divided by r. So from this I can get r, which is 85.45, and then x will be calculated as r cos 55, x equal to 49. O2c directly is 100. You can just see that 100 is there here up to this point, plus x, that is 149. Then O2d, that is this point, O2d is equal to O2c, OC 149 plus the radius, that is 234.45. This is principal stress. So one principal plane is represented by point D, another principal plane is represented by B. So OB is 149 up to C minus the radius, that will be 63.5 p2, right? This calculation I have done because I have not drawn graphically. I could do it after this calculation. I could do it with the geometry, but what you can do is you plot it directly, measure O to D, that will be giving you major principal stress, directly measure O to B, that is minor principal stress. That's all. That's how we can solve the problem. Okay. Here I have done that also, graphical method. So taking some scale, I have drawn 70 on this axis, 100 this axis, the point A is marked, this line is drawn, failure envelope, angle is measured 35 degrees, right? So origin of planes is found this way because this plane is horizontal, right? And this indicates major principal plane, this indicates minor principal planes. So when I have measured, it is 34.45 and this is 63.55, right? So do they match? 234.5 and 63.5. Yeah, exactly the same values have come, right? Because I could measure 63.55 on the AutoCAD, that's why I could measure. Otherwise in graph you can come up to 63.5 or even 63 is also okay. Around 10% error in measuring these values is fine, it can be accommodated. Okay. Now triaxial shear test. So direct shear test, direct because we are shearing it directly on a particular plane. Here it is triaxial shear test. You can just see the arrangement, very interesting arrangement is there. All right. This is soil specimen. It is a cylindrical specimen actually. So if I have to draw here itself, this is cylindrical in shape. And here on the external side it will be held by a rubber membrane. I don't know whether it is given or not, but anyway, outside you will be having rubber membrane and loading pads at bottom with porous stones, and at the top and at the bottom, and then loading base, right? So that is soil specimen. And then what I have told you is a cylindrical soil specimen with the loading pads above and below, and then there is a rubber membrane all everywhere around the specimen. And then there is a facility here, you can just see 9, a cell fluid, means water is let inside into this. So water gets into this space. So here all you will find water. So everywhere here, I'm sorry, it went inside. So here you will be having water. So water is let inside, and I should make into pieces. Okay, here I have water everywhere. What it is done is, once the water is let inside, here there is a air vent for letting the air out. So 3 is also closed once the water comes out. The 9 is also closed, right? And then there is a facility that you can increase the pressure of water. So what happens is the soil specimen is squeezed from all the sides. From the top, you can just see here, from the top, right? From the sides all around, it is cylindrical, so all around 360 degrees it is pressed, right? Okay, then afterwards there is a facility that you can apply the vertical load, right? So that load is applied so that the soil specimen fails on a axis whichever is having least strength. So it may fail like that, it may fail like this, whatever way it is free to fail along any plane. In direct shear test, the plane is defined, horizontal plane on which it fails. Here we are applying cell pressure all around so that it is in equilibrium, because when you have a specimen and you apply the same vertical pressure, there will be horizontal vertical reaction. You apply this way some pressure, exactly the same pressure this way. You apply this way pressure, that way exactly the same pressure. So this is called cell pressure, means water is applied with some stress, and generally this is denoted as sigma 3. This is applied and the soil specimen is in equilibrium, but vertically additional load is being applied till the failure uh, till the failure occurs. That is what is triaxial shear test. We'll see here. Triaxial shear test. The test was introduced by Casagrande and Terzaghi in 1936. Okay. The soil specimen used in this test is cylindrical in shape with a length to diameter ratio as 2 to 2.5. So D is equal to, D the diameter is equal to the height divided by 2. Our height will be equal to 2D, H equal to 2D. That's how the specimen is having a dimension. In this test, specimen is compressed by applying all the three principal stresses. So I have told you vertically, horizontally, two ways. So all these are principal stresses because there is no shear stress applied on these planes, on this plane, on front face. Nowhere there is a shear stress. So all these three are principal planes. The test equipment contains triaxial cell. So this is called triaxial cell. Number 5, perspex cylinder. So this is cell. Loading frame with proving ring it will be so that you know how much is the force applied at one. Pore pressure measuring device. So when you apply the load and close it, there is a facility how much is the load applied, sigma 3, right? And also here there is an arrangement. You can just see this 8. This is connected to the soil. So when you apply the force, if there is a lot of liquid here, it tries to come out. So there is a valve and there is a measuring device. So 8 is additional pore water outlet, means you can allow the water to go out from the pores, or you can measure the stress inside the pores. Okay, so there is a device to measure pore pressure measuring device. A volume change gauge is also there, right? 7, pore water outlet. So there is a outlet, there is a inlet, or on one of these things there will be a pressure measuring device, right? Okay, we'll see the detailed procedure. At the top, air release valve helps to expel the air from the cell, that is 3. The specimen is and steel plunger for applying axial force on the specimen. This is the plunger which helps to apply the vertical load. So axial load measured by proving ring there itself. The specimen is enclosed in a rubber membrane. I told you there will be a rubber membrane with porous stones top and bottom. It is kept inside the triaxial cell with loading cap on top. This is a loading cap on the top. Cell is filled with water and required cell pressure sigma 3 is applied by constant pressure system. So here there will be arrangement wherein the pressure applied is maintained at a constant rate. It is bit tricky, but you have to have that arrangement so that the pressure is always same. Now additional axial force called deviator force is applied through the plunger till the specimen fails. Means once the cell pressure is applied and it is made constant, you apply vertical pressure till the failure. So deviator stress delta sigma is noted down and sigma 1 becomes sigma 3 plus delta sigma. Obviously so here sigma 3 is there on all the axes, but vertically along with sigma 3 there will be in the direction of 1, I mean 1 sigma delta sigma is applied till the failure occurs. So vertical pressure becomes sigma 3 plus delta sigma. That's how I have written here. Sigma 1 becomes sigma 3 plus delta sigma, whereas all around it is remaining the same as sigma 3. Now with this set of sigma 1 and sigma 3 values, Mohr circle at failure is drawn. Now sigma 1, sigma 3, I have got one set. Now we have to conduct at least 2-3 tests, right? Suppose I have got 3 tests. So one set value sigma 1 over here, sigma 3 there, I have got Mohr circle that way, right? And let us say this is test A, and then different specimen is taken and then test has failed for a different set of sigma 1, sigma 3. That is that circle, the third circle, and you have to draw a common tangent line. A common tangent is drawn. Before that, I think Mohr circle at failure is drawn. The test is repeated on 3 specimens with different cell pressure sigma 3. Mohr circles are drawn for each test. So there are 3 tests. A common tangent is drawn which will be known as failure envelope. So this line is again a straight line, failure envelope. Intercept on y-axis gives you cohesion. The inclination of the line with horizontal gives you phi, the angle of internal friction. So you have to give C and phi. Anyway, how to draw circle with the values, etc. we'll see through some numerical problems. So here there is one. Determine the shear strength parameters of soil in a triaxial test. For following data, use analytical method. Check your results by graphical method. So both the methods are asked. Now what is given as a data? There is test number 1, trial number 1, test number 2. So cell pressure, that is water pressure applied, is 100. Then axial pressure directly they have given. They have not given delta sigma as such, but vertical total pressure is 250 at which the failure has occurred. Here when cell pressure is 200, it has failed at a total vertical pressure of 390. That is one more. Now here it is sigma 1 the total pressure, this is sigma 3. So there are 2 points with sigma 1 and sigma 3 and we want 2 values C and phi. So we can do it analytically like this. Okay, in triaxial test sigma 3 is cell pressure shown this way, sigma 1 is this way, sigma 3 plus delta sigma. Now sigma 3 delta sigma axial pressure, deviator stress, that's why sigma 1 becomes sigma 3 plus delta sigma. The relationship between these principal stresses at failure that is sigma 1 and sigma 3, and C and phi, we have sigma 3 is equal to Ka sigma 1 minus 2C root Ka, where C is cohesion, Ka is given by tan squared 45 minus 5 by 2 or tan squared alpha. Anyway, it is there are two unknowns. K is one unknown, C is another unknown. We know the values of sigma 1 and sigma 3, two sets. So substituting these test data, first one sigma 3 I have to substitute. Look at that. So what I have done is sigma 3 is substituted as 100, K is written as it is, sigma 1 is substituted as 350. Is it right? Because 100 plus 250 I have taken, so axial pressure at failure, so this I have considered it as delta sigma, so to say. If I consider this as delta sigma, then it is 250 plus 100, so 350 minus 2c root k, and the second one 200 sigma 3 k, and the total is 590 minus 2c root k. So here I have considered this as delta sigma rather than sigma 1. You may take it as sigma 1 also. The ambiguity is there in the data, because of that little problem is there. So you clearly write what you have assumed it to be, right? Here it is not very clear, axial pressure at failure. I think it should have been taken as a total pressure. Anyway, I have taken delta sigma. I have further calculated the sigma 1. What you would have done is, you could have done is 100 equal to K 250 minus 2c root K, 200 equal to K 390 minus 2c root K would have given you slightly different results. Anyway, solving this to C comes, Ka comes out to be 0.417. I have, I think, subtracting number 1 from 2. So 200 minus 100 is 100. This cancels off anyway. 590 minus 350 is how much? Around 240. K is equal to 100. Therefore, K comes out to be 0.417. So tan squared 45 minus 5 by 2 is K. That's why phi can be calculated. It is 24.32. And using this K value, substitute there, you will find C. So 100.417 350 minus 2C, it will be giving you 35.58 kilonewton per meter square as C. That's how the problem is solved. Anyway, if I try to solve it as a graphical way, now look here. Okay, the first one is 100 and 350. So 100 is here, 350 is there, because further 250, because these planes, now if I take this one, this is indicated as what? Now 350 the total vertical pressure, 350, and normal stress is 350, shear stress is 0. That's why the point is 350 0, that is this point. Now this plane, vertical plane, is having 100 as normal stress, sigma 3 is 100, but there is no shear stress, it is 0. So the point is 100 0, so that point is over here. And when you got two planes perpendicular to each other in specimen, right, they are diametrically opposite. Because of that, you take it as a diameter and draw the circle. That's how the circle is drawn on the same lines. So here it is shown, right? 100 is here, 100 0 becomes a point on the Mohr circle, and this is 350, 350, 0 becomes a point on the more circle, circle is drawn. For the second trial, this is 200 comma 0 becomes 1 point, 200 0 becomes 1 point, 590 0 becomes another point. Draw the circle and then you draw a common tangent, then measure the angle with respect to horizontal, that is 24.29 degrees, and the intercept on y-axis is 35.53, and they are same as the earlier results that we have found. Okay, 35.53, angle is 24.32. Okay, one more problem. A direct shear test was carried out on a soil specimen and the following results were obtained. What would be the deviator stress at failure if triaxial shear test is carried out on the same specimen? Okay, here, because it is a direct shear test, you know that normal stress and shear stress are plotted on x and y axis. 150, 110 is point number 1, so that is that I have drawn 150 and 110, then 250, 120. This is 250 horizontal, vertical distance is 120, and the Morse envelope is drawn. The angle made with horizontal is 5.715, C is 95. That is finding out C and 5. Now what they ask is, if the test is conducted on triaxial shear test with the cell pressure of 150, what would be the deviator stress? Now we'll see here this way. C equal to 90, phi equal to 5.7, then relation between sigma 3, sigma 1 is like this, sigma 3 equal to K sigma 1 minus 2C root Ka, right? Fine. Now using this here, I can calculate Ka because I know phi 0.819. Now I'll take this equation and then substitute. Look here, what we can substitute. Cell pressure is given, sigma 3 is given, so I have put 150. Then this K is 0.82, sigma 1 is not known, it is shown as it is, minus 2C root Ka. So only unknown in this equation is sigma 1, 392.75. So delta sigma is sigma 1 minus sigma 3. That's why delta sigma or deviator stress would be 242.75. Okay, we'll stop here. We'll continue in the next class. Thank you.